Now I want to explain this article, edge linear first order dependency parsing with undirected maximum spanning tree inference. So you know that dependency tree is a directed graph because you need to know the direction from head to the dependent. So but we are using a trick. We use it for an undirected, then we convert it to directed, and then we modify that. And so this article from great people in Hebrew University. So this is the first paper to address undirected inference for graph-based dependency parsing. And of course, if you like this article, then with high probability, you'll also like this article. It's pruning for cube pruning. And so the good news is that the runtime complexity of state-of-the-art inference in graph-based is not n-cubed, but it is superlinear in the number of words. Yes, it is superlinear, and you will see why. We propose such an inference algorithm for first-order models which encodes the problem as a minimum spanning tree problem in an undirected graph. This allows us to utilize state-of-the-art undirected minimum spanning tree algorithm whose runtime is just superlinear at expectation and at very high probability. A directed parse tree is then inferred from the undirected. So we are cheating. We are going from, because undirected is easy to find the algorithm for maximum spanning tree, then we infer it from the undirected. And so it's a very tricky, good idea in this article. And is subsequently improved with respect to directed parsing model through local greedy updates. Both steps are running in linear order of time, order of n in time complexity. So the time complexity is order of n, so it's linear. The inference methods that we know, everybody uses Eisner for the projective case, but not all sentences are in a projective case. So some of them, as I said in Czech and Dutch, there are non-projective cases. There are lots of non-projective cases, and so the edges cross each other. So in that case, we use CLE algorithm. But let's see what is the idea of this present paper. We want to do it better to reduce the time complexity. So we propose to formulate the inference in first-order dependency parsing as a minimum spanning tree problem in an undirected. You may say, okay, we are maximizing the score, you said. But now we are talking about minimum spanning tree. And I say by just a negation, we can easily convert from maximum to minimum. So that's not the case. That's not the challenge. Our formulation allows us to employ state-of-the-art methods for maximum spanning tree. If you look at the literature for computer science, you see lots of algorithms. So why not taking advantage of them? Why not using them? Whose runtime depends solely on the number of edges in the graph, and importantly, a parser that employs our undirected inference algorithm can generate all possible trees, projective and non-projective. So remember the work of Karger, but in order to understand the work of Karger, let's focus on the historical algorithm of Borovka, because it's the basis of the randomized algorithm of Karger. By the way, I've explained some of the algorithm of Karger in my playlist for approximation algorithm in the part that I was talking about randomized algorithm, and they are very interesting. The undirected maximum spanning tree problem has a randomized algorithm of order of m. And that is why we like this. At expectation, of course, and with a very high probability. And the worst case is order of m, and it's a deterministic case where alpha is certain natural inverse of Ackermann's function. These are very old things, but we use it nowadays for dependency parsing at the inference time, because we want fast parsers. Linguistics they push us to work on fast algorithm. They say we need lower time complexity. So the algorithm of this paper has 4 steps. First, it encodes the first order dependency parsing is in the undirected maximum spanning tree. Then it computes the maximum spanning tree of the resulting undirected graph. Then it infers a unique directed parse tree from undirected. So because you have obtained the undirected, but we infer the directed from that. And finally, the resulting tree is greatly improved. And the last 2 steps takes order of n, which makes the total runtime with very high probability, order of m. So we negate the weight, as I said, going from minimum spanning tree to maximum spanning tree. So the graph contraction, I explained this graph contraction algorithm of Boruvka in just simple. So in A, going from A to B, the origin is B, but when we choose the minimal edge for each vertex, for example, the minimal edge for this vertex is this 4. The minimal for this vertex is 1. The minimal for this vertex is 2. The minimal for this vertex is 2. And after that, the contracted graph. So we contract these edges that we have selected, put them into one supernode. And so again, this is one supernode. And you see, now there are 6 and 5 and 3 are going from one supernode to another supernode. So we just say, again, we do dynamic programming. Again, we do it again and say 3, 5, 6, which one is minimum? 3. So that's it. We've got the final results. So the 2 algorithms for undirected maximum spanning tree in the number, and these algorithms are based on substantially different. So one of them is deterministic, but the other one is randomized algorithm. And so the first one is here, the second one is here. The first one is deterministic, is very old, but let's focus on just the second one. It's a randomized algorithm, the work of Karger. And the terminology is that the heaviest edge in a cycle does not appear in the maximum spanning forest. F stands for forest, because you have lots of trees. And the cut property for any proper non-empty subset, the lightest edge with exactly one endpoint is included in the maximum spanning forest. So it's so this is the algorithm for Karger that uses the randomized maximum spanning forest. If we flip, so the randomization is here. We flip coin. If it is head, then we include that, the edges and the vertices as well. And so we have 2 problems. The problem 1 is undirected encoding, because we want to design an encoding that encodes the directionality information into the graph of the undirected maximum spanning tree. So how we do deal with that? going from undirected to directed. The second one is that once the undirected is found, we need to direct its edges in order for the end result to be a directed dependency tree. So we are making an undirected graph into directed graphs in these steps. And the local enhancement. Finally, we should improve the tree greedily for simplicity. And this motivated us to develop a local enhancement procedure that is explained in this paper. This is the local enhancement procedure. We want to enhance the edges to create a better directed graph.